It's easy to get lost in the scenery out here, but if you're in tech, data, or finance, you'll know that the hardest part of any model isn't the view. It's separating the actual signals from random noise, and that's where the p-value comes in. Suppose we have two scoops of sand, A and B. We want to see if they are different from each other. In statistics, we have to be skeptic, so we assume that they are not different, but actually the same. And we call this our null hypothesis. And before we announce any results, we need to be 95% confident, meaning that we don't want to claim that these samples are different when they are in fact the same. And the remaining 5% will be our tolerance for false alarms. It means that we have one chance out of 20 to get a low p-value even though the grains of sand are the same. And p-value will be the probability of finding a difference that big, assuming that both scoops are initially the same. So we run the test once and calculate our p-value, and there's a chance where we find it bigger than our tolerance. We call it alpha. So let's say that p-value is 0.12. It means that a difference like this can only happen 12% of the time, meaning it's bigger than our alpha. So we just slap a luck label on it and still hold on to our null hypothesis. In this case, we say that we failed to reject our null hypothesis. But let's say p-value is less than alpha. For example, we find p-value to be equal to 0.04. It means that a gap this big or this difference can only happen 4% of the time, which is way less than our alpha. So that must mean it's too rare for it to happen by random luck. So we reject our null hypothesis. However, an important note that you must remember: p-values cannot tell us how different scoop A and scoop B are. Let's say that a grain of sand in scoop A are 0.01% thinner than the ones in B, and somehow we get p-values less than alpha. Sure, it tells us that a difference this big cannot be by random luck. However, the difference is so negligible that we disregard it. Also, an important note that you must remember: there's what we call p-hacking. And let's say we took a scoop and got a p-value bigger than alpha. So we do it again and still the same p-value. And we'll do it again 100 times until we find p-value lower than alpha. And we say that these are totally different. But are they? As we said, we are taking 5% risk. So we have 1 out of 20 chance that we get a false positive. And in our previous test, we had a lower p-value. How can we be sure that it's just a random fluke even though the p-value is lower? It's because we ran one single test. That math favors us 95% to 5% that the difference is real. But if you repeat the test 100 times, you're not doing science. You are forcing that 1 in 20 fluke to happen. This is what we call p-value hacking. Let's say in a situation where we need to be a lot sure of the result, and a 5% risk is too much. We can simply just lower it. A great example is if we are testing a rocket. We need an alpha to be 0. A lot of zeros, 1% chance. That way we can have a false positive 1 out of 10,000 or 100,000, wherever suits you. But if we are testing if a bus will arrive on time, 5% chance risk is just as good. So to wrap it up, the p-value doesn't tell you how different the subjects are, and it doesn't fully prove your theory if you keep testing again and again. It just tells you how weird your data would be if you had nothing going on. Just run your test once and don't fall for p-hacking. If you learned anything, drop a like, a comment. And it's time to leave this beach.